In our last class, we just had a little bit of exposure to this new kind of arithmetic using integers. And what I'd like for us to be able to do over the next 2 class periods is to make a justification for why there is an equivalence relation at play in this example of arithmetic around the clock. Right? And so the way we'll do that is just by getting our heads back into the equivalence relation space. And here's how it's set up. So we want to discover an equivalence relation on the integers that explains the phenomena that we saw in our last class with the clock arithmetic. So in this example, we were sort of making the case down here that 12 and 36 and 60, as far as a clock is concerned, those 3 integers really occupy the same position on the face of a clock. Right? They're all up here at the top of the clock, 36. 1 occupies the same position as 37, or maybe as negative 11. Right? So each of these numbers around a clock face is not just a single integer, but it actually represents a whole bunch of different integers. Right? We could put all those different integers in those locations and still have a coherent way of doing arithmetic. So the picture that I'm trying to set up here, let's take this example of 1, negative 11, negative 35, 37, 145, ... is that each of these numbers around the face of a clock is actually a whole set of numbers. It's a set that we would call the equivalence class. So if I take all of these different numbers that belong to the 1 o'clock position on the face of the clock, and I just make them into one big giant set, comma, 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 like this, right? Dot, 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 comma. That I would call that set the equivalence class of 1. Maybe I'd put these square brackets in a 1 around it. Right? It's called the equivalence class of 1 because it consists of 1 along with every other number with which it is equivalent in this circumstance. So each of the numbers around a clock face really represents an equivalence class of integers. So our job is going to be to try to figure out what is the equivalence relation that gives rise to that equivalence class. How are these numbers, all these different numbers that are in the equivalence class of 1, what is their relationship one to another? So can you think of just a hypothesis to get your thinking started on this? What can we say is true about those numbers that explains why they all share the same equivalence class? What these numbers all have in common, teamwork, what these numbers have in common is that they're all 1 more than a multiple of 12, right? So I'm going to use Casey's notation to write that. So the equivalence class of 1 can be thought of as the set of all numbers having the form 1 plus k, such that k is a multiple of 12. Okay? So that's a way to describe this equivalence class. Right? It's all of the numbers that are 1 more than a multiple of 12. Let me bring that over onto a new page here. Oops. Equivalence class of 1, the set of all numbers that we can write as 1 plus k, where k is a multiple of 12. Let's see if we can take the observation k is a multiple of 12 and make that into something that we can operationalize in a formula. What do numbers that are multiples of 12 look like? How can I produce multiples of 12, maybe using an algebraic expression? How would I recognize in an algebraic formula an expression which is a multiple of 12? The more streamlined way of writing this set builder notation is just to write it as 1 plus 12n, where n is an integer. So that's another way of understanding this equivalence class. And it's kind of a nice way because it also gives us a 1-to-1 correspondence between the elements of this equivalence class and the integers. Right? So you give me an integer, I give you one of these numbers that's in the equivalence class of 1. And vice versa. If you give me one of these numbers in the equivalence class of 1, I can give you an integer. And that exchange is a 1-to-1 correspondence. You give me different integers, I give you different numbers on the clock, and vice versa. I give you different numbers, you give me different integers. All right. So if this is the equivalence relation that defines the equivalence class of 1, what do you think is the equivalence relation that would define, I don't know, the 7 o'clock position? what integers, or what would the elements of that equivalence class look like? What do I have to change? Yeah, rather than 1 plus 12n, because 1 was kind of my starting point on the clock here, if I were looking at the 7 o'clock position, I would just do 7 plus 12n. So if I take 7, then I go 12 more hours to 19, I would have another one. 12 more hours to 31, and I would have another one. No, wait, no, that would be 29. All right, my arithmetic is already failing me. But you get the idea. 12 more hours from that is going to give me another element. 12 more hours from that is going to give me another element. And the same goes in the reverse order as well. So 7 plus 12n. Where n is an integer. So this is defining all the equivalence classes. But we want to go one layer beneath that surface. And this is going to be your task over the next couple of classes with your group. And that is to figure out how can we tell, how to know exactly when two numbers are in the same equivalence class. So two integers, let me say it this way, two integers share the same position on the clock. So just to prime the pump a little bit here, let me take a number like 230, and then let me take another number like, I don't know, negative 142. So here's two numbers. And I'd like to know, do those occupy the same position on a 12-hour clock, or are they in different spots? How can we answer that question? One way of answering this question is to divide these numbers by 12. But neither of these numbers are divisible by 12, right, if we check. So, yeah, Grace.
If you divide by 12 and then see what the remainder is, I think that would be
Divide by 12 and then see what the remainder is, right? So when we're thinking about division here, we're not thinking of division in the sense of does it go evenly, but we're thinking about really, and this is also getting me to my next topic, applying an algorithm that can show me what is the quotient and the remainder when these integers are divided by 12. So what we're doing is kind of, not just kind of, I would say, exactly, trying to figure out the quotient and the remainder when each of these things is divided by 12. Right? So my quotient is going to be here, my remainder is going to be there, and my remainder is definitely going to be something from 0 to 11. Right? That's going to be one of those remainders, less than 12. And of course, if it's 0, then what position on the clock is it really? It's the 12 o'clock position, because 0 and 12 are in the same equivalence class. All right. So we apply whatever your favorite division algorithm is to figure this out. What is your favorite division algorithm? Long division? Why not? 12 goes into 23 once. Bring that down here. Subtract. Gives me what, 11? And then 12 goes into 110 9 times. Quotient of 108. And so the remainder is 2. And so at the end of the day, there's what I get by applying a division algorithm to 230 and 12. Okay. And then 142, we do the same thing. I'm going to spare you the details this time. This is going to give me a quotient of negative 12 and a remainder of 2. So now that we've done that division process, what do we conclude about whether 230 and negative 142 are in the same position on a clock? You say yes. Why? What are you cueing in on? How are you making that conclusion? They have the same remainder when they're divided by 12. Right. So you're looking at this 2, looking at that 2. Those are the same. So one way of understanding how do we know when two integers share the same position on a clock is that they have the same remainder when divided by 12. So that's indisputably true. I want to supersize that observation. I want to make it a little bit more palatable to doing arithmetic, because division is messy. I would much rather have a way of making this conclusion that doesn't rely on us having to apply an algorithm to divide two numbers. is there a way that I could take this observation, which is that 230 and a negative 142, when I write them both out in quotient remainder form, they both have this 2 that's sitting here on the end. Is there a way I could do something with 230 and 142 that could cancel out these 2's? So let me put a finer point on what I'm trying to say here.
Let them equal?
Kind of. So let me get that quotient and remainder back up. Our first order observation is that these 2's were the same. That's another thing I don't like is same, because it requires us knowing specifically what each of those remainders is. Is there a way I can combine these two equations together so that that sameness of remainders turns into a more easily checkable condition? I'm beating around a very large bush here, I suppose. I could just give it away, but I wonder if close, yeah. So we're ultimately, when we apply these division algorithms, there's a way of using division algorithms to discover the greatest common divisor of a pair of numbers. That, I believe, happens in this example, that the greatest common divisor of 12 and 230 ends up being 2, because this 19 here is a prime. The same as, I don't think, true of negative 142. I think it's got a 4 in it. But yeah, we're getting there. You're jumping the line a little bit. If what we care about is that those two remainders are the same, doesn't matter what they are, it just matters that they're equal, right? Then one way of removing the remainders, the specific remainders from the equation, is just by subtracting one of these equations from the other. And so what I'm going to get is, on the left-hand side of the equation, 230 minus negative 142. So minus a minus is going to give me a plus. It's going to give me 372, whatever that is. And then on the right-hand side of the equation, my 2's are now gone, right, which was the point. And my quotients, 19 times 12 minus negative 12 times 12, that's going to turn into 31 times 12, I believe. Right. And so since my remainders are gone, now I'm left with a new statement. 372 equals 31 times 12. What's important about this? Well, maybe I'll ask, what's important about the number 372 that this equation surfaces? It's a multiple of 12. Right? In particular, it's this multiple of 12, right? 31 times 12. So which multiple of 12 it is probably also doesn't matter. Probably the important observation is that it is a multiple of 12. And so if we try to generalize that observation, 230 and negative 142 have the same position on a clock because what? When I subtract them, what do I get? A multiple of 12. So that is a way to avoid having to divide anything, as long as we know how to recognize what a multiple of 12 is. Right? And there are other ways besides dividing to do that. Right? You can check that it's a multiple of 3 by adding up its digits. And if the sum of its digits is a multiple of 3, then it's a multiple of 3. You can find out if it's a multiple of 4 by taking the last 2 digits. And if the last 2 digits are a multiple of 4, then the thing is a multiple of 4. So there are other ways to avoid division. And that's always good, because in abstract algebra, we tend to try to take as little structure for granted as possible. So if I don't know that I can divide at all, then coming up with a way of doing this with subtraction would seem to be more flexible. So another way to do it is that the difference is a multiple of 12. And so what this does for us is it now gives us a test that can show us whether two numbers are in the same equivalence class. And I'll just write that down in the bottom corner of the screen here, because this is where we're going to jump off into today's activity. So two numbers x and y are in the same clock position. And we'll write x twiddle y. If x minus y is a multiple of 12. And the way to say that, right, that something is a multiple of 12 if it's 12 times an integer. Right? That's what we set up here. Right? So if x minus y is equal to 12 times n, for what n? Where does this end? So n's got to be an integer. Which integer? How many integers does this have to be true for? How many n's have to satisfy this equation? Well, in this example, what played the role of n? 31. So for any given pair of integers x and y, there's only going to be one n that's going to meet this criterion, right? It's the 31st multiple of 12 in that previous example. So, and this is something else I want us to get used to, that n, before it appears in my argument, if I just write an n here, then anyone reading this argument is not going to have any idea where that n's coming from, how many n's that this has to be true for, what, if anything, we know about that n. So we need to introduce that n by quantifying it. There exists an n, and that n has to be an integer, right? Such that x minus y is equal to 12n. And this little twiddle, x twiddle y, is an example of a relation. It's going to tell me which integers, x, are related to which other integers, y, by being in the same position on the clock. And it's an instance of what it turns out is an equivalence relation. And this is where we transition. So an equivalence relation, not just any relation between elements of a set, meets the criteria to be an equivalence relation, and therefore define equivalence classes. What three things have to be true in order for a relation to be an equivalence relation? I need three properties. Reflexive. So there's property number one. What does reflexive mean? How do you know when an equivalence relation is reflexive? What has to be related to what? X has to be related to x. For all, so I'm omitting these quantifiers, but it's on the sheet that I'm handing out. For all x in my set, x has to be related to itself. Every element's got to be related to itself in order to have an equivalence relation. So that's first property. Give me property 2, or another of the three properties. Yeah. Symmetric. And what does symmetric mean? It has to be satisfied by this relation.
If x is related to y,
Mm-hmm.
the other way? Y.
Yeah, then y must be related to x, and vice versa. So x is related to y if and only if y is related to x. Every equivalence relation is a two-way street. Right? It's more like being friends on Facebook than it is being followers on Twitter. Right? So on Facebook, if I become friends with you, then you're also friends with me, and we can see all of each other's stuff. On Twitter, if you follow me, I can't necessarily see your stuff. Right? So equivalence relations have to be symmetric. It has to go both ways. What's the third one? Transitive. And how does the transitive property read?
X related to y, y related to z, then x is related to z.
Yeah. Then x is related to z. So, in other words, no matter how long the path of intermediate relations is from me to you, if there's a path of any length that relates me to you, then we must be related by a path of length 1. Right? If anyone taking graph theory, by any chance? Graph theory? Any graph theorists in the audience? Well, if you take graph theory, if you were to list out all the elements of your set and draw lines in between those that were related, the transitive property means that all of those subgraphs would be complete subgraphs. We can't have a group that's connected without all the elements in that group being connected to one another, even by a path of length 1. So these are the three properties that an equivalence relation must satisfy. And you can check that this twiddle over here meets all three of those criteria. And the question that I want us to ask and answer this week is, what's so special about the multiples of 12 in this example? Could we take the same construction and make an equivalence relation using other sets here besides multiples of 12? So what about difference is a multiple of 6? Would that be an equivalence relation? What about multiple of 7? Would that be an equivalence relation? What about difference is a perfect square? Would that be an equivalence relation? Or what about the difference is a natural number? Would that be an equivalence relation? And that's actually where I want us to start. So with your groups, the first thing I'd like you to do is to take that natural number example. So x is related to y if x minus y is a natural number. So there is my definition of a relation. And what I'd like for your groups to do is, for groups 5 and 8, figure out whether this is a reflexive relation. Groups 6 and 9, figure out whether this is a symmetric relation. And group 7 and 10, you know what you're doing, transitive. So take 5 or so minutes and see if you can persuade yourself whether or not this relation meets the criteria that you were assigned. In order to be an equivalence relation, what do the answers to these questions have to be?
Yeah.
All 3 of them have got to be yes in order for this to be an equivalence relation. So if even one of your groups comes up with a no, then we know this is not an equivalence relation. But check your criteria, and then we'll see where we're at. Let's check in on these 3 properties when the set that I put here is the natural numbers. So is this relation, that x is related to y, if the difference between x and y is a natural number, is it reflexive?
No.
No, why not?
Because x minus x will be 0, and 0 is not a natural
0 is not a natural number. Very good. Because if x were related to x, then x minus x would have to be a natural number. But x minus x is equal to 0, and 0 is not a natural number. So that's a contradiction. Right. So this is not a reflexive relation if I put the natural numbers there. Did you come up with a way to fix that problem? Is there a way I can change this set in order to make this relation reflexive?
You could change it to the whole numbers.
Yeah, what if we just sort of throw 0 in there? And instead of being the natural numbers, it would become the whole numbers. Then it would seem this would be a reflexive relation. All right, symmetric. Is this a symmetric relation or not? No, why not?
Well, because if x is greater than y,
If x is greater than y, then what happens?
if you do y minus x, then it would come out, well, it could possibly come out to a negative number.
Yeah.
Not natural.
Not just possibly. If you make the assumption that x is greater than y, then y minus x will be negative. So if x is greater than y, then x minus y is going to be positive. It's going to be a positive integer, and therefore will belong to the natural numbers, and therefore x will be related to y, right? So if x is greater than y, then we can say x is related to y by this relation. But y minus x, on the other hand, will be less than 0, and therefore will not be an element of the natural numbers, and therefore y will not be related to x. So symmetric property is also no. Is there a way we could fix this set to make the symmetric property hold? What would we need? We would need to have all of the integers, not just the positive integers, but for every integer that's in that set, we also need its negative to be in that set as well. Right? So there's the deficiency that makes this not a symmetric relation. Transitive groups, you had the hardest work to do here. Did you figure out whether this is a transitive relation? If x is related to y in this example, then necessarily x is greater than y. It's a greater integer than y. That way, x minus y is a positive integer, i.e. a natural number. Right? So x is greater than y. If x is greater than y and y is greater than z, does it follow that x is greater than z? So, and y is greater than z. Then it would seem to follow that x is greater than z. Are we getting a yes here? I think we are getting a yes here. Right? So the number line is kind of a proof, but another way, maybe, to do this would just be to write something like, well, if x is greater than y, it means that x minus y is greater than 0. And I need to introduce a z into this equation somehow. So if I want a z in this equation, what I really ought to do is subtract it and then also add it. This is a classic old mathematical trick. When you take Introduction to Real Analysis, you do a lot of these kinds of tricks in the services of proofs, adding and subtracting the same thing. But then if I rearrange this equation to get x minus z on the left side, I can move z minus y to the right side by subtracting z and adding y. I get this. But by assumption, y minus z was greater than 0. Therefore, x minus c is greater than 0. So we actually did get a yes on the transitivity part. And so what I'm asking your groups to do next is to think about what feature of the natural numbers accounts for the no's and the yeses that we got here. And I think we already put our finger on it for the case of reflexive. Reflexivity failed because what isn't true about the natural numbers? 0 is missing, right? We really need 0 to be in there in order for reflexivity. Symmetry failed because we had positives, but we didn't have negatives, right? We didn't have things that were capable of canceling the positives. This is maybe another way to think abstractly about what that means. Why transitivity held is actually maybe a more subtle question. I would argue that one way of understanding it is to look at this equation, this little inequality we had down here a minute ago. That the difference between x and z and the difference between y and z, when I combine them together, I still got something which is greater than 0. So there may be a way to mine that for some more information. But I want to give your groups the rest of today's class to begin the exploration of the general question and try to come up with the idea of what do we need to be true about set A? What feature must A have in order to guarantee that your property, reflexive, symmetric, or transitive, actually holds in general? So if it helps, you may decide to play with some more examples. Maybe make A the set of multiples of 12, because we know that one does satisfy all three. Right? Or maybe make A the set of perfect squares. We don't know which of these that property is satisfied. So you can also play around with finite sets, like maybe A is just the set 1, 2, 3, 4, 5. See if you can make your property held satisfied in that case.